So in the knapsack example, uh, the problem is that there is a thief who breaks into a house and finds n items, and these n items are um, items with different weights. Let's say the weights are given in an array to you, and apart from the weights, we are also given a set of values, how much worth each item is. And the thief wants to steal as many items as possible. Wants to steal as many items as possible. But what's the constraint? The thief is carrying a knapsack which has a certain limit, a certain upper capacity, upper maximal weight that it can hold before it breaks. Let's say the thief can carry at most, let's say C for capacity, C pounds in his knapsack. This is the constraint, right? So the question is which subset of items to steal. So a brute force approach here would be for the thief to enumerate every single subset of items from this set, and that goes back to the subsets problem you must have done in the second week of the program, enumerating all possible subsets. Now you could add a backtracking layer on top of it, saying that if the partial solution at any stage already exceeds the capacity of the knapsack, then you backtrack. Right? It's futile to continue down that direction. So you would still have maybe several different options for which subset of items to steal, all of which fit within the capacity of the knapsack. And for each of them, then you compute the total weight or the worth of items, not weight, sorry, the value or the worth of items in that subset, and then pick the subset that has the best value. But we want to do something better than that, because even that might be exponential. Right? Maybe the knapsack capacity is reasonably high, and we still have a large number of subsets that can fit into the knapsack. So for the purpose of this problem, we are going to assume, we are going to make an assumption, and this assumption is what makes this problem a particular variant or version of the knapsack problem called a fractional knapsack. So the assumption is that the thief can steal fractions of items. So think of the steal not as stealing iPads or LG TVs, but as stealing maybe bags of sugar or salt or gold dust or something like that. Okay, so which items should the thief steal? So take 30 seconds to a minute to think about this. So Dan, just a comment, I just read it. You said your proof for the number of dimes being strictly less than 3 did not seem entirely complete. You proved that it could not be 3, but you did not prove that it couldn't be 4 and so on. So all that is included in 3, because what I'm saying is, as long as it's at least 3, it doesn't matter whether it's 3 or 4 or 5 or 6 or 7. there is improvement possible because I can take 3 of those coins and replace them with 2 coins, a quarter and a nickel. So, so that claim applies to any number of excess quarters, uh, 3 or more. Okay, so back to this problem. So one of the uh, points to note here is that even if we were to use a greedy approach, there are actually multiple strategies that might come to our mind. And just to uh, take an example here, a simple example, I'm just going to draw, I'm going to assume these are 4 items that we have. Their weights are, let's say, 5, 10, 20, and 30. Their values are $1, $60, $100, and $120. And let me also assume that the first of these is present in, there are 10 copies of this. So for this particular example, so whatever greedy strategy we come up with, we should apply it. And the first attempt could be something like this. Since I want to increase, so what's my objective function? My objective function is to uh, maximize the value, total value of the knapsack items. Right? The thief wants to steal as many items as possible with the hope that the overall value will be maximized. So that's the objective under the given constraints. So since we want to maximize the value, the you know the one of the greedy approaches we could use is to pick the most valuable item first. So the thief is making a sequence of choices, and the first item that goes into the knapsack is the one with the most value. So that means uh, the item with weight 30 and value 120 goes into the knapsack. Now there is still, and we'll assume here that the knapsack capacity is 50 pounds. So that's the upper limit. So 30 pounds have already been put. We have 20 pounds remaining, but we focus on the item with the most value among the remaining items. So since the item with this item has already gone in, the item with the which is the most valuable among the remaining would be this one. It has a weight of 20 and a value of $100. So the weight now is exactly 50 pounds. The value is $220. Okay, so that's what this greedy algorithm leads to. Second way to be greedy is to do something slightly different. Maybe the thief thinks, I don't want to break the knapsack, so let me start with the lightest item first. So that way I can pack in as many items as possible and hope that I'll get the maximum value out of that. So pick the lightest item first. So by that, according to that strategy, we would pick all 10 copies of this item first. So that means we would have a combined weight of 5 plus 5, 10 times. So we would fill our knapsack with all 10 copies of this item, but the total value would be 10 times a dollar, which is $10. By comparing these two greedy strategies, you can see that clearly this one is much worse because the lightest item also happened to be almost worthless. So even though we got 10 items instead of getting 2 items, the combined value was much less. So that's the most. So far it looks like picking the most valuable item first is the best strategy. Uh, Now the question is this the really the best strategy? Uh, so if the problem had been um, another version of the knapsack problem, it's called the 0-1 knapsack. So the 0-1 just means that you have a binary choice. Either you pick an item or you leave it completely out. Either take the item or leave it behind. So the question is this the best we can do? So by observation here, if you want to maximize the value of the combined value, the total value of the knapsack, uh, it looks like what's the best you can do? Yeah, this is the best you could do, $220, but um, anyway, we'll come to that 0-1 knapsack a little later. But it looks like this strategy seems to pick the best uh, uh, subset of items for the 0-1 knapsack. Now, the fractional knapsack problem tells you that you can break apart items and put fractions of them also into the knapsack. So that means we are allowed to, um, if I wanted, I could break apart this 30-pound item into two. I could pick 15 pounds of this, uh, 20 pounds of this, 10 pounds of this, and then pick one copy of this if I wanted to. So another, a third way to be greedy is to, since picking the most valuable item first, uh, might also cause the knapsack to be filled quickly, right? You can imagine there being an LG TV which is quite valuable, but its weight is so big that it fills the knapsack completely. So in that case, we won't have any space for other items. Picking the lightest item first might also lead to a problem because if we pick items that are worthless, then that also might not optimize our value, overall value. And so what if we picked so imagine that we are making choices here for every unit weight, right? We have C pounds to fill in the knapsack. For every pound we are thinking, what fraction of what item should I add next? So the first pound, if I had only 1 pound, a 1 pound knapsack, which item would I pick? Um, so that means we have to ask which fraction, which 1 pound fraction is has the most value. So we have to take the price and we have to divide it by the weight to see what is the price per pound. And that would be another way to be greedy. Pick the item with the highest, you can say, value density or price per unit weight. So what are those values here? So price per unit weight here is $4 per pound. This is $5 per pound. This is $6 per pound. And for these items, it's 1 by 5. So that's $0.2 per pound. So clearly, this item is the most valuable per pound. So maybe it's uh, a more a more branded version of salt or something like that. So we'll clearly fill in the the first pound of our knapsack with a piece of this. In fact, if we had 6 pounds available or even 10 pounds available in our knapsack, we would fill all 10 pounds of the knapsack with a with an item whose price per unit weight is the maximum. So we are getting the most value for the weight that we are filling in. And once we have exhausted it completely, then we move down to the next item in terms of the price per unit weight and fill in as much of the knapsack as possible with this. And then once both of these have been filled in, so let's account for that. We've picked the 10-pound item and we also picked the 20-pound item. So we got $60 and $100 from that. Then we move down to the next item in terms of the price per unit weight. And here we have the total item being 30 pounds, but we've taken up 30 pounds already from our 50-pound knapsack. So we have 20 pounds left. This item is 30 pounds. So we can break this item and take 2/3 of it to stuff it into the knapsack. So we'll take 2/3 of this item, which means we'll get 2/3 of the value. 2/3 of 30, and we get 2/3 of the value. So the weight now is 20 plus 20 plus 10, 50 pounds. Here the weight is, so the value is, so this is 40, 40 times 2 is 80, 80 plus 60 is 140, 140 plus 100 is 240. Now if you notice here, this $240 is more than $220 and it's much more than $10. So among these three greedy strategies, it looks like picking the item with the highest price per unit weight has been the most profitable. Ignore the 0-1 knapsack for now. We are focused on the fractional knapsack here. So the question is, how do I, is this the optimal strategy, or could there be some other greedy strategy I don't know about which could produce something even better than this? And plus, I'm just using this example here. What about a general example? How do I know which strategy will lead to the best outcome in a general example? So for that, again, I have to come up with some kind of proof. Why does this greedy strategy work? Right, number 3. The claim is that it works correctly. So let's follow the same line of argument. Suppose it doesn't work correctly, which means our greedy strategy picked a certain sequence of, I shouldn't say items, we made a certain sequence of choices for where the next pound should come from in the knapsack. And the optimal algorithm also made a bunch of choices, but they were not necessarily in this order. Right at the end, whatever it was, we just lay down those choices and try to align them with our sequence of greedy choices. So this is our actual sequence, and here we've just laid down those values, the optimal solutions pieces, you can say, aligning them so that again we have a bunch of values that are common. And then in the greedy strategy, we have picked some, we made some choices which were not made by the optimal algorithm. The optimal algorithm might have made other choices. Since each choice here represents 1 unit weight, the number of red points here must be equal to the number of green points, right? And the total number of points in either set must be exactly 50, or whatever, C, where C is the capacity of the knapsack. So let's look at the first point of difference, assuming all of these are the same. Let's focus on uh, a particular choice we made in our greedy algorithm, for which the corresponding choice, now we don't know which of these green points was aligned with the red one. All that we are enforcing is that wherever they match, right, whatever is these common points are, they have to be aligned. Now, which red point aligns with which green point, that's, just assume that it's just some arbitrary mapping for now. So what is there any problem we see here? So one claim we can definitely make is that this red point corresponds to a price per unit weight. The price per unit weight for whichever item was that red item, for the red item fraction, must be greater than the price per unit weight for the optimal, or you can say the green item fraction which is aligned to it. Well, why is that? Because so either they are the same or one of them is bigger than the other, and we are assuming they are not the same. So is it possible that the price per unit weight for this could be smaller than the price per unit weight for this? The claim is it's not possible because we are exhausting every item with the largest, with a higher value of price per unit weight before we start chewing away items that have a smaller price per unit weight. Right, every single item with a higher price, every piece of every item that has a higher price per unit weight is put into the knapsack first. So it's not possible that we left out something of higher price per unit weight uh, in our greedy algorithm. So that's why this, if they are not the same, this must be a strictly greater than inequality, not less than. So in that case, you can imagine taking this and replacing one of these green points with this red piece, right? In fact, you can pick any of these green pieces. The claim is that all of them will have a price per unit weight that's smaller than this red piece. Otherwise, we would have picked them. Our greedy algorithm would have picked them first. So we can replace this green piece with the red piece, and by doing so, we would be increasing the value of the optimal solution, because the price per unit weight for that 1 pound has now increased, which means the combined value would increase. And that should be impossible because we are assuming that this green piece belongs to an optimal algorithm. So it can't be greater than, it also can't be less than. That means the two have to be the same, which means there cannot be a like a deviation between the greedy algorithm and the optimal algorithm in the set of choices that were made by both. So this is basically a proof by contradiction again, by which we have shown that this greedy strategy of picking items in decreasing order of price per unit weight will always work for the fractional knapsack problem. So what about the 0-1 knapsack? Suppose we had more constraints here. Either we pick an item completely or we leave it behind. So that's a stricter constraint. We can't just, we don't have the flexibility of picking fractions of items. So in that case, what would we have done? Our greedy strategy would have picked the first two items, but this last part we wouldn't have been able to do this. So our combined weight in the knapsack would have been 30 pounds. Our combined value would have been $160. Well, we couldn't do this. Maybe it would have come down to this, and then maybe we would have added 6 of these as well. No, sorry, how many? We've reached 30 pounds, so we have 20 more pounds left. So yeah, we would have added 4 copies of this. So maybe $4 more. But still, it wouldn't have been 240. In fact, it wouldn't have been even 220, which is something we know we can do with a different greedy strategy. Okay, so it looks like this is the greedy strategy that, at least for this example, worked for the fractional for the 0-1 knapsack problem. The greedy strategy, which was optimal for fractional knapsack, did not work for the 0-1 knapsack. Now the question is, does the greedy strategy which worked in this example for the 0-1 knapsack work in general? Pick the most valuable item first. Well, we can see. Let's pick an example. So we are trying to evaluate the 0-1 knapsack. With a greedy strategy of picking the most valuable item first. So let's construct an example where we have an item that has a value of $100 and which perfectly fills the knapsack. And then let's make two other items that are $60 each, but which don't fill only half the knapsack. Right. So this is a simple example where if we apply this greedy strategy of picking the most valuable item first, and our capacity C is still 50 pounds, we would fill all of these 50 pounds with this $100 item. This would be the greedy strategy. Whereas we know the optimal strategy would be to pick the two $60 items. right? 25 plus 25 pounds. That's $120, which is better than what this greedy strategy did. So it was just that specific example where it so happened that for the 0-1 knapsack, this particular greedy strategy worked. By just tweaking that example, uh, we have come up with another counter example, a different counter example where the first greedy strategy is nullified. In fact, all three greedy strategies have been nullified for the 0-1 knapsack. We saw that strategy number 3 did not work for the 0-1 knapsack example that we took here. And strategy 1, which worked on this particular example, did not work on this example. And strategy 2 also did not work on this example. So that means none of these three greedy strategies solve the 0-1 knapsack problem. And so that is why in the dynamic programming section of the course, we solved the 0-1 knapsack problem using dynamic programming instead of any greedy approach. But if the problem had been a fractional knapsack version of the knapsack problem, then this third greedy strategy, as we proved, is the one that will always work. Any questions on this? So the fractional knapsack is the classic example of a greedy algorithm in computer science. Nagesh?
Yeah, thanks, Omkar. We have mentioned here that this choice of the price per weight of for the red item is greater than the price of weight for the optimal with the green item. It
Yeah.
is impossible. If you could a little bit maybe clarify that, I missed the point there. Why that cannot be the possibility here?
So it's impossible because what we can do is by replacing, I'm just going to call it the green pound, right? That we are just talking about that 1 pound uh, piece of the knapsack, right? By replacing the green pound by the red pound or the 1 pound weight, uh, we we will improve the optimal solution, right? Which should
Yeah.
not be possible since it's optimal.
Oh, okay, okay. I got it. So that's by contradiction. Yep, yep.
Nivedita?
Thanks.
Sure.
Yeah, I have a question about the 0-1 knapsack. The third type of greedy approach will work if you have like unlimited amount of supply of each of the item, right? So this didn't work because you have a limited quantity of each of the item.
Uh,
Because when you see for the 10 pound item, which is of worth $60, if you go by the third greedy approach, right, per pound weight, which is higher. So if you choose like 5 of this item, then the per pound weight multiplied, it will become like if you choose the 5 items of 10 pound, it will be like $300. So that will be the most valuable item, right? Compared to the other approach where we took the 30-20 combined of 220. So why don't we go for that?
So there will be other examples where, uh, so I'm not sure about this unlimited version. Um, Given that, for practical purposes, we have n items only. You're saying if n was made infinity.
Yeah, here, which means the 10 pound item is, there is only one item of weight 10 and worth 60. That's how we are dealing with this problem, right?
Hmm.
Like the first item is alone, we have like 10 times of that item, but the rest of the three items are like one item.
Right.
Okay. Okay. So
Um,
that
so yeah, I'm not sure that it would work for the unlimited version. Let me think about it after. Let's come back to this after taking a few more questions,
okay.
because I'll also take a break. So if you don't come back by that, I'll try to think about it during that 5 or 10 minute break.
Okay, sure.
I don't have an immediate answer, but I think that there will be some other example we can construct where that might not work. But I don't want to like take up time right now thinking about it. I'll think about it over the break.
Yeah,
Rohit,
yeah.
sure. Any other questions, Nivedita, or was this the only one?
No, that's it.
Okay. Rohit?
Hi. So here the values dollar 160, 100, 120. These are actually in a sorted values, and the weights are as well.
Yeah.
But then when you calculated fraction and the second value came up $6 per LBs, I'm just thinking programmatically how we will figure out that second value we have to choose for third option. So I'm talking about the third option, about the fraction one.
Hmm.
That $6 is the value that we have to choose here.
So we are basically going to sort these items in decreasing order of price per unit weight.
Okay. Okay.
So having done that, we will um, try to put as much of each item as possible in the knapsack when we traverse that reverse sorted array.
Okay. So this fraction will also be in assorted values, right?
This fraction will always, sorry, what?
So we will store this $6 per LB, $5 per LB, $4 per LB in a reverse sorted array, and
Yeah,
then
so it
we
depends on
will.
how the input is given. If the input is given to you, if these two arrays are given to you in the form of a single array of pairs, right? W comma V, W1 comma V1, and so
Yeah.
on, then you could just sort that array in place, reverse sort that array in place, but you would need to set the comparator function to look at the density, I mean the value density, the price divided by the weight, price per
Yeah.
unit weight, sort based on that. If they are given to you as separate arrays, then you would probably need to use extra space to uh,
To divide them
compute
up.
and store the price per unit weight first, and then uh, then sort based on that.
Okay.
Normally, when this is given to you, we'll look at a problem which is not exactly fractional knapsack, but something similar to it. They will give it to you together in a single array of pairs.
Right. So the divided values may or may not be, so divided values that will come out, the fraction may not be in a sorted output.
May not be. They will have to be reverse sorted based on that.
Okay.
I mean, the sorting has to be done in reverse, in decreasing order of price per unit weight,
You're
because
right.
this is the primary order in which you are implementing the greedy approach. How do you pick the best possible choice? Even in the coin change problem, we were looking at the coins in decreasing order of denomination.
Right.
So in general, for any greedy strategy, one common way of implementing it is going to be to sort based on whatever we want to maximize or minimize on, right? Whatever that metric is that we are trying to pick the maximum or the minimum for, we'll sort based on that, reverse sort or forward sort. And if we don't have access to all of them at the beginning, then we might have to dynamically uh, pick them by putting them on a heap. Whatever we have available, we put them on a heap, and then as we discover new items with those metrics, we keep adding them to the heap. So the greedy algorithms that I have covered for graphs in the advanced graphs section for the minimum spanning tree problem and the shortest path problems, those greedy algorithms use heaps because when you're given a graph, you don't really know which edge is going to be relevant. That depends on what your partial solution up to that point is. So there you would implement the greedy approach using heaps. Here we are implementing the greedy approach by sorting everything in advance. Even in Kruskal's algorithm, where the edges had to be looked at in increasing order of weight, we first pre-sorted all the edges in increasing order of weight, and then we looked at them. So either sorting or using heaps. One of these two will be the typical implementation of a greedy algorithm.
Depending upon whether we want to save the space or we want to have better time.
Well, not just save the space, but also for you will use heaps when you don't have all the data in advance, or when you don't know all the data in advance that will be relevant to the problem. Like in the minimum spanning tree example, like until you have constructed part of the spanning tree, you don't know what set of edges are going to be relevant to pick from. So that's why Prim's algorithm looks at what edges are on the fringe and then picks the edge with the lowest weight from the fringe. So that is something that can only be dynamically decided because the fringe is not a static thing. So you need a heap for that.
Yeah.
If you haven't gone through that section, you can keep this comment on the side and then notice its relevance when you go through that section.
Yeah. Thanks.
Ramya?
Can you explain why the third strategy didn't work for the 0-1 knapsack? Sorry, I missed it.
So in this example that I constructed, I tried to construct this example so that the most valuable item is an item that's filling the entire knapsack, right? But there are two smaller items, not as valuable as this, but both of them together fit into the knapsack.
Yes. So
you're asking about the third strategy,
right? I meant like
okay, this one.
Yeah, I mean we said this is the value per pound.
Okay. Yeah, so that didn't work even on the first example here because so in the first example, what we did is according to the third strategy, we would have picked the 10-pound item and the 20-pound item. Both of them would completely fit into the knapsack. So we picked these items and we put them. The value so far is $160. Does that make sense? We
Yes.
picked this one because this was $6. This was $5 per pound. We are able to fit both of these. Now, after this, we will next examine this and we see that its weight is 30 pounds. Since we already have 30 pounds in the knapsack and we have only 20 pounds capacity left, we can't fit 30 pound item. And in the 0-1 knapsack version, we can't break that item, so we would have to drop it. We would have to ignore it. And then we would move finally to the last set of items here, which are almost worthless. So it doesn't really matter how many of them we can fit into the knapsack. That's not going to change the value by much, just $4 or so. So our value here for the 0-1 knapsack would just be, for the 0-1 knapsack, it would just be 60 plus 100 plus 4 times 1, I think. So 164. That's what this the third strategy would lead to.
Got it. So that's because we either pick the whole item or we don't pick it.
Yeah.
Got it.
Now that's suboptimal compared to the $220 we got from the first greedy strategy.
Yes, I got it. Thank you.
Yeah. But the first greedy strategy doesn't work on other examples of 0-1 knapsack. That's why even that's out. So that means none of these three are going to work in general for the 0-1 knapsack problem. Emmanuel?
Yeah, so I was just going to follow that up with for the 0-1 knapsack, you use dynamic programming, but for fractional knapsack, you would use greedy approach.
Yeah. Yeah.
Yeah, so before this class, I was thinking that the one way of differentiating DP versus greedy was um, if if you have certain choices and all the weights are the same, I would use greedy. But if the weights were different and you want to optimize or maximize that, I would go with like a DP approach. That was my mind state.
Yeah,
Like,
that doesn't work even for the minimum spanning tree problem where the weights of the edges could be all different.
yeah,
But the greedy strategy is what works there.
okay.
And even here, for the fractional knapsack, if the weights, it doesn't matter whether the weights are the same or different here. Assume they're all different. The greedy strategy is what works. Sekal?
Yeah, so basically I was going to, can you please clarify the part? So we have several greedy strategies, right? And the idea of which of the items worth more like $6 item 10. So if we take first, if we feel them that one first, taking 5 of them, that would be what greedy strategy would be that?
That would still be,
Or it's not a greedy strategy. In my understanding, it should be one of the greedy strategies, right? When we fill with items which worth more, $6 in this case.
yeah, so that would be a greedy strategy where we are being greedy on the price per unit weight.
Right, but I cannot see that case when we fill with 5 of 10
Yeah,
pounds.
because there is only one copy of them.
So we can use each item just once?
Yeah, so in this particular example, we are assuming that there are 13 items in the house. There's one copy of these and then 10 copies of this item.
Oh, I see. Now I get it. Thanks.
Yeah. It's not like coins where we assume we have an unlimited number of.
Yeah, got it.
Okay, so answer one question and also reply. I think someone asked about whether we are on time for the agenda. Well, actually no, we are going much slower. But at the same time, this is the first time I'm teaching this topic or any of these floater topics for that matter. So the time calibration isn't something that is known in advance. Unless you teach it, and if it's a hard problem or if there are subtleties which lots of people don't understand, then you have to recalibrate. So if there's anything that doesn't get covered today, I will, it'll just get pushed to the next class. But we'll end up covering everything. So I had mentioned that I will think over the question that was asked by someone here, whether for the 0-1 knapsack problem, if we had an unlimited supply of these items, would strategy number 3 work in that scenario? And the answer is no. I had suspected the answer is no. I was able to construct an example where it doesn't work. So I'll just give that here. 0-1 knapsack, greedy strategy number 3, with the added assumption of an unlimited stock of each item. And let's just pick 2 items here. Let's pick an item with a weight of 35 pounds, whose price is $350. Okay, there's an unlimited supply of this. So maybe I can draw it like that. And then there's another item which has a weight of 25 pounds. And there's an unlimited supply of that. Its worth is $200. So when it comes to the price per pound, you can see that this is $10 per pound and this is $8 per pound. Let's assume that our capacity is 50 pounds as before. Capacity of the knapsack. So what the greedy strategy would do is to first stuff the knapsack with as many items as possible with this price per unit weight. So that means we would pick the 35 pound item, only one copy of it, because 2 copies of it would exceed 50 pounds. So we would have $350 worth of items in the knapsack, and then we won't be able to stuff any more of this item. So we would then move to the next item, and here this item has 25 pounds weight. We don't have that much capacity in the knapsack, so we stop here. So this is what the greedy strategy would terminate on. It would give us $350 of value in the knapsack. Whereas the optimal strategy, you can see here, is to pick 2 25-pound items, which would have a combined value of $400, which is better than the third strategy we used. So the bottom line is that for 01 knapsack, we go for dynamic programming, not for a greedy strategy. For the fractional knapsack, we use the strategy that picks the item with the maximal price per unit weight first. Subbu?
Yeah, hi, Omkar. Yeah, I'm just taking one example. Let's say I have three items with 10 lb, 5 lb, and 1 lb, and the price of 10 lb is 100, and 5 lb is 50, and 1 lb is 100, 10. In that case, I'm seeing that knapsack one is that a knapsack is working for a greedy solution, right?
Yeah, so you might see that the greedy strategy works on some examples, but like in mathematics, just because some formula you think that works in general applies to some specific values of n, doesn't mean that it works in general unless you have a formal proof for it, because a single counter example can disprove it. So
Okay.
a greedy strategy might work on many examples, but even if there is a single counter example where it doesn't work, then it's not a correct algorithm.
Yeah, it's based on values, right? We can.
Yeah.
Okay.
Yeah. The coin change problem we did was not specific though. We picked a specific denomination of coins, but we allowed the amount to be arbitrary.
Yes.
So in that sense, it was specific, but at the same time, not very specific. It was a general problem. Whereas here, picking up specific examples of for capacity, specific examples for weights, that would mean it's an individual example. Because in the knapsack problem, the capacity also is allowed to vary. It's a general C, and the weights are also allowed to vary.
Okay. Thank you.
And Emmanuel?
Yeah. So for greedy algorithms, I've just meant I know certain patterns like job scheduling, and like now the fractional knapsack, and I guess the coin change. But for like dynamic programming, you kind of start out with decrease and conquer, and you kind of arrive at a recursion equation to come
Yeah.
up with for a solution, even if you've never seen the problem before.
Yeah.
For greedy problems, if you've never seen it before, where do you start and how do you approach that kind of questions?
Well, since your goal is to maximize or minimize some objective function, you would try to start in a way that your very first step is the best possible step that you could take. If you are allowed to take only one step, um, you would ask yourself, where would I rather be, at the end of that step, knowing that I might not get all the way there, but you're just allowed to take one step. So you would just focus on that local, first choice. So like that's what I did. If I had only one pound to fill in the knapsack, the first pound. Of course, I have more, but if I just focused on the first pound, where would that first pound come from? Which item would it come from? Likewise, if I had only one coin to pick, I want to minimize the number of coins, but if I had only one coin to pick, which coin would I pick? Would be the coin with the highest denomination, so that I get as close as possible to the amount.
Yeah, but I was getting into, like, in order for you to think that way, you kind of assume you have to kind of go that greedy path, right? Like,
yes.
My question is, before even that, decrease and like conquer, like right away from there, you can see some kind of overlapping problems. You can construct a recursion in dynamic programming that will lead you to the DP solution. I'm saying before you even go down the greedy approach, what leads you there?
So obviously it's not clear what leads us there, and plus, as we just saw, there are many different ways to be greedy. In this case, in this problem, two of those approaches did not work. One of them worked. So it's a very hard. I don't think there is like a generic answer to what. How would you decide whether the problem is solvable using a greedy algorithm? That you don't know until you try something, and until you're able to prove something. In general, it doesn't work. We know. But dynamic programming also is a type of decrease and conquer where you can say that you are first relying on your subordinates. Well, before that, you have multiple choices to make. So even if you were to just focus on the first step, in a dynamic programming based approach, you would consider all possible ways of filling that first pound or that first coin, not necessarily one particular way of filling it. Right? You would consider all possible choices you have there, and then you would rely on someone else to come up with the best solution for the remaining set of blanks, and then combine the individual costs of each of your steps with the costs of all the solutions that they come up with, and then pick the one with the best. Whereas in a greedy strategy, you're kind of doing decrease and conquer, but you're only decreasing it in a greedy way. That means you'll have only one choice you will make, and it's that choice you've made which will keep growing, right? That single partial solution is what will keep growing. So it's a very different style. It's not something you can think of it recursively, because it is decrease and in a decrease and conquer way, but it's not like dynamic programming where you would have multiple choices with potentially overlapping subproblems. There are no overlapping subproblems if there's only one choice you're making, because there's only one subproblem.
Okay, got it. Thank you.
Shobit?
Yeah, Omkar, just a thought. If the value density is just like the American coins, so then greedy approach might work, right? Because then it will be kind of similar problem. Or is that wrong?
Yeah, it might, yeah.
Right?
Yeah.
Okay.
So Yeah, I mean, you stuff in as much as possible. Again, depends on whether it's 0-1 knapsack or which
So
one you're talking about.
that brings me to one question for the coin problem. Let's say if we don't have 1 cent, like my point is, if we are not able to make like any number, like it is not every time possible to make every number with a smaller denomination, will the greedy approach still work, like in general?
You mean if it was not
Like,
if it was not like, because with a 1 cent denomination you can
yeah,
work
that's what
number.
I was asking. Like, if let's say there was no 1 cent in American problem, like, so then will the any greedy approach will work, or we have to move to DP for that? So why I'm specifically saying 1 cent is, let's say we are not every number is possible to make with that denomination and all.
Yeah, I don't like. I'm not sure that a greedy approach will work in that case, because the general case was to rely on 1c, c squared, c cubed, and so on, or like the Roman numeral example I was giving, where each successive number is like a certain number of units that you group together to form the next higher denomination, and the amount then has to be reachable by using the most basic unit in the general case. So yeah, otherwise, so then I would use DP if it was not as restricted as that. If it was a more general problem, I would use DP.
Okay, thank you.
Saikal?
Yeah, I'm also having a problem with during the interview, just to be safe, choosing the greedy approach. So for example, in this particular example with unlimited items, can I assume that it's safe to go with greedy approach if weight of the item is lower, but its worth is higher? Like, let's say, like in previous example, we had 10 pounds, but it worth is highest, right? Like $6 per pound. So in this case, can I go with greedy approach?
So
Like-
in the general case, you should go with the greedy approach if it's a fractional knapsack problem, not for a 0-1 knapsack, because in the 0-1 knapsack problem, you won't be able to make specific assumptions like that. And if you want to work with very specific assumptions, then you have to come up with your own proof that a greedy approach would work.
But is there any general assumptions about greedy approach that it will always work? Like,
No, only for fractional knapsack, not for, and for say the American coin changed or 1c square, that those specific examples, not for the general coin change problem, not for the knapsack problem with these additional constraints, the binary choice 0-1.
so basically you're saying that if we have unlimited items and 10-pound item which costs higher than all the other items, like $6 per pound, basically it weighs less but costs more. So in this case, it's a wrong assumption that we can use greedy approach. That's what you're saying?
Yeah.
Okay, thanks.
Yeah, because I was able to construct this example, so it's only. Yeah.
No, this example right now, 25 is lower than 35, but the cost per pound is lower as well. But what I'm saying is that when when its weight is lower but cost is higher, like in previous example. So in the previous example, if it would be unlimited, can I assume that it's safe to go
Yeah,
with-
but then the problem is that these were just two items, right? If there are 10 items, you would have 10 choose two different pairs to compare, right? Is the weight lower and the price higher? I mean, then it becomes, it's not like there are only two items here, so the analysis might work for this, but it's not necessary that the smallest item will have the highest or the smallest weight item will have the highest price in general for the, when there are 10 examples. Even for the intermediate ones, it's not necessary that there'll be a linear ordering.
I see. Okay, thanks.
Okay, the third example we want to take up is this one, where you're given a chessboard, and I'm assuming you all remember the n queens problem. So on an 8x8 chessboard, what is the maximum number of queens we can place without any of the queens attacking any of the queens? Well, the answer is 8, because you're able to place those 8 queens successfully in multiple ways actually. So on an 8x8 chessboard, if it was asked what is the maximum number of kings that we can place where none of the kings attack each other. Okay, so we want to place as many kings as possible on a chessboard such that none of the kings attack each other. Now, how does a king move? In case someone is not familiar with chess, so if we have a king on any of the any cell of the chessboard, a king can attack any of the 8 neighboring cells. So either here or here, 3, 4, 5, 6, 7, and 8. So it's this local region that the king can attack. And so we want to place as many kings as possible on this chessboard so that no 2 kings are attacking each other. So let's take a minute to think about this. So our objective function is to maximize the number of kings on the chessboard. So on an 8x8 chessboard, given that there are 64 cells, we can place a king on each of the cells. But there are constraints given here, which is that no 2 kings should attack each other. So that limits our choices, because placing 64 kings is not a feasible solution. So we need to place the kings so that they are not attacking each other. So let's actually think of what we would do if we were asked to place as many kings as possible just in the first row. We were to just take the first row, and instead of an 8x8 chessboard, let's imagine this is a row of 8 cells. We want to place as many kings as possible on this cell, in this row. What would you do? Well, let's say I start out with 1 king being here. Now the next king that I want to place, I would want to. So why did I start out with the first king being as far left to the as possible? Because I want to squeeze as many kings as possible in this row, and so I don't want to leave any blank space at the end in case more kings can squeeze in the middle. So I take my first king, place it at the extreme left, and then I will place my next king again as much to the left as possible. So I can't place the king literally next to the first one, and so I'll place the next king, second king here. The third king will go there, and the fourth king will go there. So in alternate columns, essentially. So 4 is the maximum number of kings that can be placed in a single row. And so the greedy strategy was to, leave as little space as possible, free space, just pack as much in as possible. Now let's focus on the 8x8 case. So if we look at the second row here, assuming that the first row has been filled in this way, the second row actually cannot be populated by any king, because no matter where we place any king here, it will be under attack by some king. So that means the second row has to be left empty. The third row is safe from any of the kings in the first row. So we could again pack the third row with kings like that. But that means the fourth row would have to be kept empty. The fifth row would then have to be stuffed with kings like that. The sixth row would be empty. The seventh row would be filled in like that. Now the question is uh, this greedy approach leading to an optimal solution? And the answer in this case happens to be a yes. This is 16, which is the number of kings we've placed here, is the maximum number of kings you can place on a chessboard such that they don't attack each other. Now, what's a little different about this problem is that the proof that it's not possible to do any better than this is a little different in structure. It's not like where we have a sequence of choices for what to construct, and then we look at whether the optimal solution made or didn't make that choice. So here's a different strategy, and a different strategy is something like this: to show that 16 is the best we can do. We can look at the territory of each king. So each king has these three cells, the neighboring three cells, as this king has the neighboring three cells as its territory. So let's make this belong to him. The next king, let's say, has this territory. The next king has this territory. So we carve out these 2 by 2 subgrids as sort of 16 territories within the overall chessboard. Now the claim is that we cannot have more than 16 kings. So the claim is that there cannot be 17 or more kings placed on this chessboard, satisfying the constraint that there are no two kings that are attacking each other. Now, why is that? Well, so here we are directly looking at the solution and we are claiming definitively that we can't do better. And we do that by noticing this pattern that each king seems to be located in a symmetric region. And then we ask ourselves, is it possible for there to be 17 kings? Or if there were 17 kings, then there must be two kings that are placed in the same region. Right? Even if I'm not thinking about the 17th king being added to this solution. I'm saying even if we were to rub out all the kings here, if we keep these regions the same, it's not possible to place 17 kings on this chessboard in any way, because there are 16 regions, and if there were 17 kings, there must be at least two kings that lie in the same region. So that's an example of what's known as the pigeonhole principle. So the pigeonhole principle says that if there are n pigeonholes and n plus 1 pigeons to be placed in these pigeonholes, then there must be some pigeonhole which will have more than one pigeon. It's a very trivial statement, but it has some sophisticated applications. There must be some pigeonhole with more than one pigeon. And so instead of pigeonholes, we have territories here, and if there are n territories and n plus 1 kings or more than n kings, there must be some territory with more than one king, and that's going to lead to a direct attack, right, or a check. So uh, so this greedy approach did work for this problem. Now there are alternate solutions which are also solutions we could have come up with. If we had filled the last row first, we would have come up with this arrangement. If we had filled in the first row starting from the right end, we would have come up with this arrangement. So it doesn't matter. Uh, the point is, we have proved that the algorithm is doing the best possible thing just by looking at the output and not comparing it in a with some other optimal solution. We just assume that if there was an optimal solution, uh, there would be an extra king, and that extra king would go into some territory with another king, and that would be a, you can say it's a proof by contradiction again if you want to connect it to what we did, but um, we don't have to look at it as a proof by contradiction. You can also make a definitive statement like this. Any questions on this? Okay, so this looks like a straightforward application of the greedy approach again, and proof that the greedy approach works is by contradiction. If there were more than 17 kings by the pigeonhole principle, two kings would be at least two kings in the same territory, which violates the constraints, which means the solution is not really optimal. Shobit, you had a question?
Oh no, sorry, I forgot to.
Somard?
Hi. I think thanks for the explanation. My trouble is, how do you translate that into the code to prove it? You cannot verbally, to walk through that. Is there any ways?
So we can't prove it in the code, obviously. We would have to first prove it and then we would write the code.
Yeah, so let's say in the pseudo-code, how do you translate this,
So this is a proof by correctness. It's not the algorithm itself.
Okay.
So the algorithm itself would start by, actually this is if you just had to return the total number of kings, you could even return it in a mathematical, as a mathematical calculation instead of, literally placing each king. But if you had to place each king, you would start with the first row, and whatever we did with the first row, you would do that with every alternate row.
Okay.
And so the number of times you're able to place the king before running out of space in that row, if you sum all that, that would be the total answer.
I see. Okay. Okay. Thanks.
So you can do this in a mathematical way, or so another way to answer your question is, if we did not use a greedy approach, we would have 64 choices for the first king. Right? Actually, even if we looked at a single row, we would have 8 different choices for where we can place the first king. And then based on that, we would have 7 choices for the second king. Maybe we would do backtracking to eliminate 2 of them. And so on. So, right. So we can also think of this in a brute force way where you literally, do what we did with the n queens. There, of course, we were not trying to maximize the number of queens. We were just trying to find a way to place them. But here we have an unlimited supply of kings and we are trying to place them in a way. But a greedy approach will not look at multiple choices. It will just pick one choice and stick to it and just keep growing that. And so what we are trying to do is to simulate the placement, or carry out the placement of the kings. That's what we would do in the code. Right, skipping one cell in the row and alternate rows, skipping alternate rows. So it's just one solution that keeps growing. Pramod?
Yeah, I just want to clarify one thing. In that slide, should it not be if there are more than 16 kings?
Sorry, yeah. More greater than or equal to 17, which is yeah.
Okay, thanks.
Thanks. Surjit.
Hey Omkar, thank you for the class. This proof actually makes sense, and yeah, I was able to understand the proof. But one thing that is kind of little confusing me is the way we arrive at the territory for each king. If we look, we initially in the beginning we said that the king can kind of like he can attack in all 8 directions, right? So if you look at it, the one region of the territory is kind of shared between 2 kings, right?
Yeah. So when I say territory, I mean so we are looking at the symmetry of this arrangement here, and we are saying that if we had to carve out a territory for each king, not saying that the king can't attack by the rules of chess outside that territory, but it's like every king gets that much space for himself. So that's the allotment of regions we are doing, and we are saying, can we do better than that? Well, if we keep the regions the same, we know that more than one king can't be in the same region, and so that's the maximum number of territories we can have. So that's the process. We come up with an arrangement. We wonder whether this greedy arrangement, is the best. And based on the symmetry, we ask whether it could have been possible to do better. But based on the symmetry, we say that it's not. And the pigeonhole principle, we say that it's not. Now, this is not something obvious. Which is why I'm taking greedy algorithms as part of this ad hoc class. It's not like you can come up with a general rule for proving any greedy algorithm correct. So there are some things that are common, but then there are multiple strategies. Like this strategy is a proof by contradiction. In that sense, it's similar to the earlier strategies. But here we are not lining up the kings or lining up the spots chosen by the kings and then seeing where there is a deviation. We are directly looking at the final arrangement and saying that we definitely can't do better than this.
Okay, so can we solve the n by n queen problem in a similar way using greedy approach?
So there wouldn't be a regular arrangement like this though for n queens. So like where would you, how do you know where to place the next queen? Here we can predict where each king will go in each row. That's why we can translate that into code very easily. There you can't have two queens even being in the same row or the same column. So then I mean, you have to capture where you're going to be placing those pieces as a general pattern for you to be able to code it up and or even calculate it mathematically. With n queens, that's not possible, which is why uh, we don't have a greedy strategy for that.
Okay. Right. Sure. Thanks, Omkar.
Okay. So we have looked at here three different examples of greedy algorithms from computer science. Actually, these are not just from these programming interview sites. They're found in computer science books. So all three of them. So we have, I mean, if you've gone through advanced graphs, you would have seen some greedy algorithms already on graphs. For example, the single source shortest path problem and the minimum spanning tree problem both had greedy algorithms. There were actually multiple greedy algorithms for the multiple minimum spanning tree problem that were correct. And even breadth first search for finding shortest paths on an unweighted graph is really a special case of Dijkstra, which is a greedy algorithm. So in that sense, BFS is also a greedy algorithm. And there also we had to prove them correct. And the style of proof was not like the style we followed for this n-kings problem, but it was similar to the, you can say, the earlier problems and even the n-kings problem, in that we used a proof by contradiction, even in those advanced graphs videos. And we showed that every step, every piece that the greedy algorithm adds, whether it's to the minimum spanning tree or to the shortest path tree, is part of the optimal solution. Because if it was not, then we would be able to again follow a similar argument, just line up the first place where the optimal algorithm makes some other choice and prove that any deviation there should be impossible. So we followed that strategy, but maybe now if you go back to those videos or if you go through those videos, in case you haven't already, you might see more commonalities between that and what we have done for the three problems today. Okay, the next problem we want to take up is this one. So this is part 2 of the problem that we have covered in one of the array floaters on, I think it was decrease and conquer. The context is the same. You are given an array of stock prices on n consecutive days, and this data is available to you. So it's as if you can see the future. So it's given to you in advance, and you want to find the maximum profit that you can achieve by buying and selling one stock as many times as you like. Now you cannot have or hold multiple stocks. Right? It's just a single stock that you're allowed to hold at any time. So if you want to buy a stock, you have to sell the existing copy of the stock first. Right? Of course, if you want to buy it, you can opt to hold it. You can opt not to sell it, but you cannot buy a second stock. So just as an example here, if these are the prices on 6 days of a stock, the best you can do is to buy on day 2. So buy here sell on day 3, and then buy on day 4 and sell on day 5. So the profit here is 4, the profit here is 3, so total profit would be 7. That's the best you can do. In this second example, where the price of the stock keeps growing, you buy it on day 1 and then sell it on day 5. So that's profit of 4. If the stock is continuously decreasing, then you don't buy it at all. So there's no profit in that case. The first part of the problem, which has been covered in one of the array floaters, is on asks you to maximize profit, but you're allowed to make only a single buy and sell transaction. So that problem was solved using a plain decrease and conquer approach, which happens to be known as Cadane's algorithm, but you don't even need to know what Cadane's algorithm is or means. You can just use a plain decrease and conquer approach to get the optimal solution there. If you actually think about it, even a brute force approach there, if you were allowed only a single transaction, even a brute force approach there would be quadratic in complexity. You have to just try every possible, pick any pair of days, and you can do that in n choose 2 ways. N choose 2 is order n square, and for any pair of numbers you pick, pretend that you're buying on the left day and selling on the right day, and just check what the profit is, and then pick the pair of days with the highest profit. So the brute force approach there also leads to a quadratic complexity, which we could improve by following a decrease and conquer approach. What would be a brute force approach here? Here we are allowed to have any number of buy and sell transactions. So when we start out on day 1, I actually have a choice whether to buy or not to buy. Suppose I didn't buy. So let me make that here. So buy or don't buy. Right, that's the choice on day 1. Then on day 2, whatever I have bought, I could either hold or I could sell. And if I have not bought, then on day 2 again I have a buy or don't buy choice. Right, and if I'm then on day 3, depending on which of these scenarios I'm in, if I'm holding, I could continue to hold or I could sell. And if I have already sold, then I again have a buy or don't buy choice. If I bought, I have a hold or sell choice, buy or don't buy choice. So for every day, I actually have 2 choices. And that means the sequence of options that I have is 2 to the power n, order of 2 to the power n. That's the brute force. And it leads to a combinatorial explosion, as you see. So we could follow a brute force approach, try every possible path down this exponential tree, and see which path leads to the maximum profit, and return that as the answer. So that's clearly suboptimal, and so we want to improve that. But hopefully this shows you that this is a combinatorial optimization problem, because there's a combinatorial explosion of options and we are trying to build a sequence of choices a sequence of decisions here that overall maximizes the profit. So in a greedy approach, we want to maximize the profit. That's our objective function. And so we are allowed to look ahead, but we will look just locally ahead. We don't want to look too far ahead. Otherwise, if on every day, if we are looking too far ahead, that's going to be, just looking at all the prices in the future would be a quadratic time thing. We want to do this in linear time, like the first part of this problem, first version of this problem. So on the first day, what can we do? Should I buy or should I not buy? So this decision, the first day's decision, is something I could decide based on what the price will be the next day. So I just pretend that I have to make that local decision. I don't care about the global problem. Just that local decision. What will happen tomorrow? If the price tomorrow is going to be more than the price today, then I should buy and then sell tomorrow. If the price tomorrow is going to be smaller than the price today or maybe even equal, then I don't need to buy. I mean, I shouldn't buy if the price is going to be less, if I want to maximize the profit. Okay, so I'll go down one of those two paths, not try both. So let's say the price is more tomorrow. So I go down this buy path. On day 2, I again have to make that local decision. Should I hold or should I sell? So, okay, for that decision also, I could look at the price on the next day. Is the price the next day going to be more or less than the price today? If it's going to be more, I will hold. If it's going to be less, I will sell. If it's equal, it doesn't matter. But again, I pick one of these two paths to go down in. Maybe the price is going to be less the next day, in which case I will sell on day 2. Then on day 3, again, I have the buy or don't buy decision to make. And if the price on day 4 is going to be less than the price on day 3, then I don't buy. And so on. So I just build one single path down this tree all the way till the end on day n. And that's the greedy approach. Now, why will this greedy approach work? Is this the best possible thing we can do? So the claim is that the greedy strategy works correctly. Why? We can again give a proof by contradiction. Suppose our solution here is not optimal. So one thing we are doing is whenever the price on the next day is going to be more than the price today, that's the greedy approach. Whenever we see the price next day as being higher than the price today, we either buy the stock or continue to hold it if we already have bought it. And whenever we see the price going down, we sell it, or we don't buy if we don't already have the stock. So that means uh, every single rise, every single uh, rise in the stock price is counting towards the profit. So if the optimal solution is, if this is not the optimal solution, where would the optimal solution differ from our solution? It can't include, it can't include a section of the, or any particular day, can't capture the profit on any particular day which is not already captured by a greedy algorithm, because every single instance of this type is already part of our greedy solution. So the only place where the optimal solution can differ is that it includes a fall which is not included in our greedy strategy. But if it includes that a fall, then by not holding the stock across that, those 2 days, we can further improve the optimal solution. Our greedy algorithm never includes a fall. Whenever we see the stock price fall, we either don't buy it or we sell it if we already have it. So that means any optimal solution can't differ from our solution in having any extra rise in the stock price. It also can't differ in having any extra fall in the stock price. So that means our solution must be equal to the optimal solution. Every single drop is missed, deliberately missed, avoided, you should say, because we are deliberately in our solution. The optimal solution cannot have a drop and cannot miss rise in the stock price. Otherwise, it could be improved, which is impossible. Hence, it is identical. Optimal solution is identical to the greedy solution, or at least equivalent. Sounds, we might, if there is a particular day on which the price doesn't increase or decrease, it doesn't matter whether we are holding the stock or not holding it. It can't do any better. Bhagesh?
Omkar, if you can go to the problem statement quickly. There is nowhere it has been written what could be the sequence of buy and sell here, right? So can you? There is nowhere written that you should first buy before you can sell.
Yeah, but initially you don't have any copy of the. So yeah, you can't sell before you buy. So yeah, that's.
I mean, that's never, because there is no condition like that given here, right?
Yeah, but they're not talking about, sophisticated options like that.
Okay. Yeah, because
what I was thinking that as per the example number 3, we could actually sell those on the day 1 and bought on the last day, so we could have get the maximum profit there.
Yeah,
like a
yeah,
bear
that's
market.
yeah, that's not yeah, so that's not assumed. That's something you can't do for this simple arrangement. So you're
Okay.
physically buying the stock,
Yeah, before you
you
can sell.
hold it and then you sell it. That's the assumption.
Okay, thanks.
Charanya?
Hey, Omkar. Yeah. So, what question that I had was, suppose there was a possibility that if I had the number sequencing that the prices per day is not in any order. So, is there a possibility? So, I either hold or sell. If I probably, the numbers could fall way down further in the days, then I could have bought there. Then probably more profit in that case. So, how does this greedy algorithm ensure that like the optimal solution, there's no difference, because sometimes it could be the numbers are arranged in such a way that it could be that if I had bought when it went even further lower, instead of sell, I hold, then I could have probably had more profit.
Yeah, but that's because so here you're allowed to complete any number of transactions with no penalty. So it's not. I mean, in real life, you would be taxed if you sold and then bought quickly, capital gains and all that. So that's not short term versus long term capital gains. All that is not a factor under consideration here. You basically are allowed to buy and sell any number of times you want, and you can even see the future. So that means every single gain in the graph you want to lock in, and every single drop you want to avoid. So you buy and sell in a way that you capture all the growth and avoid all the drops.
Okay, so I have one more question. So in the first, the zeroth element, how do I choose whether I buy or don't buy? So do I always choose buy?
It depends on the price the next day. So the way this algorithm would be implemented is you have a bunch of days for which the prices are available. So on each day, so on day 1, right, day 1 actually would be index 0 in the array. So on each day, you're looking at the next day, the price on the next day, to figure out what to do. So let's say for day varying in the range from 0 to, I won't say n-1, I'll say n-2, because on n-1, day n-1, there's nothing to look forward to in the future. So for each day from 0 to n-2, you look at the price on the next day to decide what to do. So if the price on day +1 is more than the price on that particular day, you're assuming that you will buy or hold, right, if you already have it. In either case, you're going to lock in that profit. So the profit would be increased by whatever amount the price grew by. So initially, of course, your profit is 0. And then at the end of the for loop, you would have locked in all the days when the stock price grew into your profit. So you return your profit at the end.
Sure, thanks you. This helps, thank you.
Yeah, so there's no sorting involved here because things are already sorted for you. Otherwise, you would have to have that additional sorting step like in the fractional knapsack problem. Or even in coin change if the denominations were not given in decreasing order. and then you do a linear pass. Here we just do a linear pass and we are done. So the time is order ends, no auxiliary space. Abhishek?
Yeah, Omkar. So, as part of the proof, you're mentioning that the solution that the greedy approach will take is equivalent to the solution that the optimal approach will take.
Yeah.
But with respect to the implementation and the algorithm itself, is it correct to assume that greedy is just taking one of those paths and reaching that solution, whereas the optimal is looking at everything and then finally coming to that solution, right?
We don't know what the optimal algorithm is. Somehow, there is some person who's claiming that he or she found an optimal solution that is better than ours.
Okay.
So we are completely agnostic about what that optimal algorithm was, whether it was greedy, maybe greedy in some other way, maybe it was DP, maybe it was branch and bound, or whatever it was.
Okay.
You just imagine that it exists, there is a better solution, and we prove that it cannot differ from our solution.
Okay, so effectively for the optimal part, we just somehow know the solution, that this could be the best solution and we cannot do better than this. And then somehow we try to map it to our greedy approach and prove that that's the correct.
Yeah, we look at any point of difference between the greedy approach and the optimal approach, and say that we can improve the optimal approach. In fact, we could have even written this in the way we did. We wrote the proof for the first two problems. Just line up whatever sequence of decisions you made for the greedy approach. Just line up those decisions, and you line up the decisions made in the optimal solution. So the question is, if from day 1 to day 2, do you possess the stock or do you not possess the stock with you? So you can argue that the optimal solution must do the same thing. If the price on the next day differs from the price today, then these two values cannot differ, because if they did, then the optimal value can be improved.
Sure. So what I was trying to put is just we might not know the optimal algorithm, but we somehow know that this is the optimal answer.
Yeah. We don't know the optimal. That's why we are trying to design the optimal algorithm. We are claiming that the algorithm we've designed is the optimal. So obviously we don't know what the optimal algorithm is which led to the optimal solution. In fact, there may not even be a polynomial time algorithm. Maybe it was arrived at by brute force by someone. So it doesn't matter.
Sure. Thank you, Omkar.
Rohit?
Yeah, just trying to understand the definition of grading algorithm here, because today you said that in greedy algorithm, we make choices very locally and we don't refer to other values. We don't go to the sub problems, but here we are going to the next.
Local means next. Only up to, just the local environment, like in the max or the min cost path or whatever that problem was. There also, there was a grid given to you, and there were a bunch of values placed here. You had to start from here, and you had to end here, and you had to pick a sequence of cells moving only to the right or downwards. You have to find a path from here, the min cost path from the start cell to the end cell. So a greedy approach there was to, I have three choices here. Well, not the third one here. There's two choices, I guess. So I have two choices to make here. While a dynamic programming approach would make both choices, right, compute the answer for both choices, a greedy approach would evaluate the local cost of making these two choices and then pick the one with the better cost and just stick to it. So we are looking here also, we're looking at the next cell. After whatever cell we are at, we are looking at the neighboring cells, two neighboring cells in 2D here. We are doing that in 1D here.
Yeah, now this clears the doubt of the local word for me. Thank you.
Emmanuel?
Yeah, so I have two questions. The first one is, what if you have an increasing sequence of numbers, like for example, 3, 5, 6?
Yeah.
Wouldn't it make sense to buy on 3 and sell at 6, but the local would give you to buy on 3 and sell at 5? And the second question is, what if there's a limit? You can't have multiple transaction, maybe like you have 3 or 4. There's a limit of transaction you can make.
Yeah, so if there's a limit, that adds constraints, which makes the problem harder. And so then a greedy approach won't work in that case. So your first question, how do you choose between holding or selling? So that the decision that we are making on on day one is just whether we buy or sell. Whether we buy or don't buy. The decision for day two, whether we sell on day two or whether we hold, that will be made on day two based on the prices for day three.
Oh, okay, I got it.
Yeah. Okay, so that completes this problem. Yeah, so like I said, each day there are two decisions to be made. Two out of this, maybe don't buy also is a decision. And we just look at the price of the stock on the next day. This problem could have been solved using a decrease and conquer approach also, but I'll leave that to you to think about. Okay, the next problem is a problem where you are asked to load a certain number of boxes onto one truck. The problem description is actually verbose and confusing, so let me just read it. You're asked to put a certain number of boxes into one truck. You're given a 2D array of box types, where box types I is number of boxes and number of units per box. Number of boxes is the number of boxes of that type, and number of units per box is the number of units in each box of the type I. You're also given an integer truck size, which is the maximum number of boxes that can be put on the truck. You can choose any boxes to put on the truck as long as the number of boxes does not exceed truck size. Return the maximum total number of units that can be put on the truck. So let me translate this in terms of something like a real world problem. So I happen to have been like a collector of Playmobil toys. Playmobil is like a brand like Lego, and my son, when he was in preschool, he used to play with it. So I had purchased a number of themes, and they happen to retire those themes every year. So a new set of toys come out every year, and so I accumulated a lot of them, and I had to sell also many of them. So let me give an analogy mapping this to selling toys like Lego or Playmobil. Now, as you know, there are Lego or Playmobil toys that are small in size, and then there are ones that are big in size. For example, there's a Playmobil theme, the Egyptian theme, where there's a huge box which can be used to build an Egyptian pyramid. There are also toys which are minifigures that are so small that they would fit into a small box. So the box sizes are very different for different toys, even within a particular theme. Now, what you have here is you have a truck. It could be something like, say, a U-Haul truck. Maybe you're moving from one home to another and you want to transport all your toys. And in this truck, there is a fixed capacity. So let's say truck size is the maximum number of boxes, crates, that you can fit into that truck, and they are all of the same size. So let's say you have 10 boxes that can fit into the U-Haul truck. Your goal is to transport or to fit into the truck the maximum number of toys. Right? We are not trying to maximize the value or minimize the number of boxes or do anything else. You're simply trying to maximize the total number of toys that can be put on the truck. Now, suppose I had only two, suppose truck size was just one. That means there's only one box that can be loaded into the truck. And let's say I have two boxes. One box has two copies of the Egyptian pyramid, and the other box has, let's say, 50 copies of an Egyptian, minifigure, a soldier or a villager, something like that. So that box can have, so the specification would be that there are two types of box types. The first box type has 2 units in that box. The second box type has 50 units in that box. Not just that, you also have multiple boxes containing those toys potentially, right? Which means it's possible that I can have 2 boxes with the pyramids. That means I would actually have 4 copies of the pyramid, maybe side by side. So when you think of box types I, think of it as a particular type of toy, say an Egyptian pyramid. This is the number of boxes you have when everything is packed in, maybe 2 boxes, and maybe only two of those pyramid toys fit into that box, because the box size is, the toy is big, so you can only fit 2 of them in. Maybe some other box type, the Egyptian soldier box type, has only one box. You have only one box, but it has 50 units of those toys. So if my goal was to transport the maximum number of toys, it doesn't matter whether the toy is small or large, which box would I choose? I have, let's say, 3 choices. I have 2 boxes of with the pyramid and 1 box with the minifigures. Which of these 3 boxes would I pick to put into the U-Haul truck if there was only space for 1 box and I wanted to maximize the total number of toys that can be put into that truck? So the answer is clear. I would pick the box with the minifigures because there are 50 of them. So I would be transporting 50 toys instead of 2 toys. So I hope that gives you a sense of what we are trying to do here. We want to transport as many toys as possible from one location to the other. I'm not sure if looking at this example is going to convey the intuition, because these are just numbers. Right, so this would be something like maybe a pyramid. Instead of a pyramid, maybe the Roman Colosseum is a big toy that you have only one copy of it that fits into a box, but there are 3 boxes. You have 3 of those toys. This one could be maybe a circus, which is a medium-sized toy, so you can fit 2 of them in a box, and there are 2 boxes that you have here. This one could be a smaller one, maybe a small like a merry-go-round, maybe an individual small toy, relatively small, where I could have a value of 50 for the minifigures, right? In some other example, see if there are, maybe this is a minifigure. Right. So I hope now everyone understands what the context of the problem is.